Presentation on the screen. Do you see it?
Thank you. Да, yes. Thank you very much.
Okay, so I will move it. ¿Cómo la cambio? ¿Con este?
Okay, so we can start, yeah?
Yes, I can start.
Okay, so let's continue our session. And the next speaker is Viktor Rykhlov. And the title of his talk is on multiply completeness of root functions. of certain classes of ordinary differential pencils of operators, please.
Before I begin my talk, I would like to express my gratitude to the organizing committee of the conference for the invitation to participate in this conference. Please excuse me for my bad English. For the convenience of the conference participants and a better understanding of the content of my talk, I wrote my talk in more detail. How can I change the page?
You tell me and I change it. Should I change?
The second.
Okay, you tell me when I should.
The second page is the content of my talk. The third page.
Okay, third page.
Problem statement and background and definition. Section 1. The main object considered in this talk is an ordinary differential polynomial pencil L of lambda in the space L2, 0, 1, generated by differential expression 1 and linear independent boundary conditions 2, where lambda is the spectral parameters, alpha aj, beta ij are arbitrary polynomials in lambda with complex coefficients. We can assume that the boundary condition 2 are normalized, that is, have the form 3. The coefficient is complex. Kappa I is the order of I boundary condition. Fourth. The total order of the boundary condition 3 is denoted by the letter kappa, 4. The problem is to investigate n and m-fold completeness in the space L2, 0, 1, where m from 1 to n inclusively, the system of eigen and associated function, or briefly the root function system of the pencil f of lambda. The differential expression L y of lambda is supposed homogeneous, that is PIS is equals 0 when j plus s less than n. Let the set of eigenvalues be lambda. It is supposed that it is countable. Let the corresponding system of root functions be y. Fifth page. Definition 1. The root function system y of the pencil L of lambda is called m-fold complete in the space L2, where m from 1 to n, if from the condition of orthogonality of the vector function h from L sub 2 super m to all derived according to Keldysh m chains corresponding to the system y, the equality h of x equals 0 for almost everywhere x from 0, 1 follows. Here L sub 2 super m is defined by the formula 5. The fundamental work on this problem is the work Keldysh, published in 1951, in which a theorem on the n-fold root function completeness was formulated without proof for the pencil L of lambda generated by a differential expression with a special principal part with variable coefficients and lambda independent splitting boundary conditions when some of the boundary conditions are taken only at the end 0 of the segment 0, 1 and the rest at 1. 6. From the result Khromov in the doctoral dissertation in 1973, it follows that this theorem is valid in the case of analytic coefficients of the differential expression. Independently, this result in the case of analytical coefficients of the differential expression was obtained by Eberhard in 1976. Shkalikov in the same year established this result in the case of summable coefficients of differential expression. A generalization of this theorem to the case of finite dimensional perturbation of Volterra operator was made by Khromov in 1977. The case of an arbitrary principal part of differential equation was considered by Freiling in 1984 and Tikhomirov in 1987. In the works of Gasimov and Magyaramov and Shkalikov, related to the general form of the pencil L of lambda, sufficient condition for n-fold root function completeness in L201 are obtained in terms of the power boundedness in the parameter lambda of the Green's function for the pencil L of lambda on some rays in the complex plane. The next page. I don't see. The detailed study of the pencil n-fold M and n-fold completeness for the pencil with constant coefficients of the differential expression whose boundary conditions are semi-splitting and independent of lambda was carried out by Vagabov in the 80s. The author managed to obtain a new result in solution of this problem in the case of the pencil L of lambda with constant coefficients and boundary conditions as splitting and also polynomial depending from spectral parameter lambda and some classes of non-splitting boundary conditions. Consider the equation 6. Assume that the roots omega k of its characteristic equation 7 are pairwise distinct and non-zero. We call omega k characteristics for short. The system of function 8 is a fundamental system of solution of the equation L of y lambda equals 0 for lambda does not equal 0. The next. Section 2, classification of the pencil L of lambda according to Shkalikov. When studying the multiple root function completeness for the pencil L of lambda, an important role is played by the class to which L of lambda belongs, namely the class of regular pencils or irregular ones. The methods for studying these pencils depend significantly on this. Therefore, it is necessary to first classify pencils. It is very convenient to use the approach proposed by Shkalikov in 1983. In the case of differential expression 1, the fundamental system of solutions has the simplest form 8, clear exponents. And the classification is greatly simplified and becomes finite, unlike Shkalikov's classification in the general case. Let us introduce the following column vectors from J from 1 to n connected with the boundary conditions. Vectors 9, 10, 11. For brevity, the lambda argument will sometimes be omitted. Next. Let us introduce the set omega 12. It's the different sums of characteristics. Then the characteristic determinant of the pencil will have the form 13, where the coefficient f omega lambda are finite sums 14. Here f sub j super omega are determinant independent of lambda. It is known that non-zero eigenvalues of L of lambda are zeros of delta lambda. Specific values of eigenvalues or their asymptotics are not required below. We denote lambda minus 0 as lambda 0. Next. Further, we use the following we denote the 15 is used for the function 16. Use this notation. For A from 0, 1, and so on, kappa, by M delta kappa, we denote the convex hull of those points omega for which F omega of lambda in square brackets R is not equal identically 0. It is clear that inclusion 17 are valid. We briefly denote the polygon M delta kappa as M delta and call it the characteristic polygon of the function delta of lambda. It should be noted that M delta is exactly the conjugate diagram I bar delta of an entire function of finite degree or exponential type delta lambda represented as 13. In accordance with the definition from the book, Levin, distribution of zeros of entire functions. Similar to Shkalikov, we give the following definitions. Next. Definition 2. A pencil L of lambda is called regular in the sense of Birkhoff-Tamarkin, if M delta 0 equals M. Shkalikov in 1983 noted that the definition of regularity 2 of the pencil L of lambda is equivalent to the definition of regularity according to Tamarkin in 1917. And naturally, such regular pencils are called regular in the sense of Tamarkin. In the special case of ordinary differential operators, this irregularity coincides with the regularity according to Birkhoff. Definition 3. The pencil L of lambda is called almost regular in the sense of stone, if M delta kappa equals M. The pencils that are called almost regular in the definition 3 are a generalization of one class of ordinary differential operators that were studied by order n equals 2 by Stone in 1927 and the general case by Khromov in 1962 and Benzinger in 1970 and 1972. Benzinger called such operators regular in the sense of Stone. The next. Definition 4. The pencil L of lambda is called weakly irregular or normal in the terminology of Shkalikov if a polygon M delta kappa has at least 2 points of tangency with M, and the perpendiculars drawn from some fixed interior point to the sides of M on which the point of tangency lie. If the point of tangency is angular, then there are 2 such perpendiculars. Divide the complex plane into sectors of angle less than pi. That is, the pencil L of lambda is weakly irregular if there are at least 3 rays in the lambda plane that split the complex plane into sectors of angle less than pi, and on which the resolvent of the pencil L of lambda has at most a power growth. The class of weakly irregular pencil L of lambda, given by the definition 4, was introduced by Shkalikov in 1983 and was called the class of normal pencils. This class is significantly wider than the first 2 classes. It follows from the results Shkalikov that if the pencil L of lambda is from this class, then the root function system is n-fold complete in L2, 0, 1. The next. Definition 5. A pencil L of lambda that does not satisfy the previous definition is called strongly irregular. See figure 1. In figure 1, the polygon M is indicated by the black line, and the polygon M delta is indicated by the red line. and the perpendiculars are the I don't know how to say the line. The next. The class of strongly irregular pencils includes pencils whose resolvents have exponential growth in sectors of the complex plane of angle greater than or equal pi. The study of multiple completeness of root function system for pencils from this class presents the greatest difficulties and has been carried out only for individual sets of pencils L of lambda. The next. Section 3, generating functions and the scheme of proving of multiple completeness. The main concept below is the concept of generating function. Definition 6. The function j of x and lambda defined for all x from the segment 0, 1 and lambda in complex plane will be called the generating function for the root function system of the pencil of L of lambda if the functions 18 are the root functions for the pencil L of lambda corresponding to the eigenvalues L nu of multiplicity S nu plus 1. The solutions of the equations L via lambda equals 0 are usually taken as generating functions. That is, the generation functions is a combination of exponential of the form 8. The fundamental system of solutions. The next. Therefore, let us denote mj of x lambda equals conjugate diagram of j of x lambda, the formula 19. It is clear that mj x lambda is a polygon. We introduce the set mj equals convex hull of mj x lambda for when x from 0, 1. Let us call mj the characteristic polygon of the function j of x lambda. From the point of view of the scheme of proof, multiple root function completeness is preferable to generating functions with the most compact characteristic polygon in the following sense. Definition 7. We will say that the generating function jx of lambda satisfies the condition alpha if m delta has at least 2 points of tangency with mg and the perpendiculars drawn from some fixed interior point to the sides of mg on which the points of tangency of m of delta lie. If the point of tangency is angular, then there are 2 such perpendiculars. Divide the complex plane into sections of angle less than pi.
Next page.
The next. In the figure 2, we can see which returns to the strongly irregular pencil. The polygon M is indicated by black line. The polygon M delta is indicated by the red line, and the polygon MG is indicated by the blue dashed line. The polygon MG is closer to M delta as M. The next. From the it is The formula 21 shows the derivative m chains for the root functions of L of lambda corresponding to the eigenvalues L nu for multiplicity S nu plus 1. The standard scheme of proving of multiple completeness, abbreviated as the PMC scheme, is based on the following lemma. Lemma 1. If generating function j of x lambda belongs alpha and h of x is orthogonal to all derivative m chains corresponding to the root function system y, then under the additional condition of orthogonality h of x to some finite set of vector functions, the equality 22 holds, where h m j of j lambda is determined by the formula 23. The next. Consider the meromorphic function 24. This function formally has poles at the point lambda nu from lambda, but if the assumption of lemma 1 are satisfied, all the poles of this function are compensated by the numerator. That is, this function is an entire function of finite degree. The fulfillment of the condition alpha for the generating function j of x lambda means that the function 24 satisfies the Fragment-Lindelöf principle. The PMC scheme for the pencil L of lambda assumes the existence of some set of generating functions j I of x lambda, I from 1 to r, satisfying condition alpha. Then, based on lemma 1, we obtain the identities 25 under the condition that vector function h of x is orthogonal to all derivative m chains corresponding to the root function system and possibly to some additional finite set of vector functions. If the set of generating functions is sufficient to obtain from 25 the relations 26, then it means that there is m-fold root function completeness for the pencil L of lambda in the space L2, 0, 1, which possible finite defect. The next. The essential condition for the described MC PMC scheme is the presence of a sufficient number of generating functions gi of x lambda from alpha. When studying the spectral properties of differential pencils, generating functions of the form 27 are usually used. Such functions were used by Naimark, Shkalikov, Vagabov, and so on. These functions, which we call classical generating functions, are entire functions in lambda, linearly independent for x belongs 0, 1, and lambda is not in lambda. The generating functions of the form 27 have been successfully used in the study of pencils L of lambda with splitting or semi-splitting boundary conditions under some additional assumption on the characteristics. The same. The next. Carrying out the above described scheme of proving the multiple root function completeness for the pencil L of lambda becomes much more complicated or does not work at all if either gi of x lambda does not belong L or does not satisfy condition is condition alpha for all I from 1 to n. That is, the function Hm of ji lambda have exponential growth at least in the half plane of the lambda plane, or it is problematic to derive equalities 26 from the sets of relation 25. Following the described scheme in this situation, it is not possible to obtain M multiple root function completeness and L201. To expand the capabilities of the described scheme for proving the multiple root function completeness, the author proposed in 1996, see details in the paper 1, to use generalized general functions of the form 28, where it's a linear combinations of the classical generating functions, where gamma 1, gamma 2, gamma n is parameters. We denote gamma lambda vector of these parameters. The next. For the function gx lambda gamma, it is also convenient to use the representation 30 as determinant. 30 in the form of determinant, where the column vectors u, j of lambda are defined by the formula 9. In particular, it follows from the formula 27 and 30 that the classical generator functions are a special case of generalized generating functions, namely the equalities 31 holds, where ei from 1 to n are unit vectors. The following lemma is valid. Lemma 2. For any lambda from the set C minus lambda 0, the functions g of x lambda gamma j, g from 1 to n, are linearly independent with respect to the variable x from 0, 1, if and only if the vector functions gamma j of lambda, j from 1 to n, with respect to lambda, are linearly independent. The next page. Next, by omega j, sub j, we denote the set of those points from omega that can be represented as omega j plus dots that is contain the number omega j as an addend. By omega super j, we denote the set omega minus omega sub j. That is those points from omega that do not contain the number omega j as an addend. Expanding the determinant 30 along the first line, we obtain the representation 32 for the function j x lambda gamma, where the vectors with heads have the following form, 33. It is convenient to assume that the vector gamma lambda is a vector polynomial in lambda, and components are represented by the formula 34. The next page. From formula 42, it is clear that generalized generate function j x lambda gamma is an entire function of finite degree in lambda. For such a function, the characteristic polygon was already introduced, since for refixed pencil L of lambda, the form of this polygon is determined only by the vector gamma of lambda. We call it the characteristic polygon of the vector parameter gamma of lambda and denote it by m gamma of lambda. that is by definition m gamma of lambda is equals m gamma of point lambda gamma of lambda, formula 35. It is quite clear that inclusions 36 are valid. If g of x lambda gamma belongs alpha, we say that gamma of lambda satisfies the condition alpha. And we write gamma belongs alpha. Thus, from the PMC scheme, it follows that gamma of lambda is from alpha, then under the condition of orthogonality of the vector function h of x to all derivative m chains corresponding to the root function system and possibly to some individual finite set of vector functions from L2, 0, 1, we obtain by the lemma 1 the identity 37. It is clear from the above that when choosing the vector parameter gamma of lambda, one should be guided by the fact that the polygon M gamma is as compact as possible, as close as possible to M delta. The next page. Section 4, sufficient condition for multiple root function completeness using the generalized generating functions. An important role in constructing the generalized general functions are played by the vector parameters v j of lambda and w j of lambda. This is connected in particular with the fact that in formula 32 for the generalized general function, in the case of gamma of lambda equals v j of lambda or gamma of lambda equals w j of lambda, a great many exponents vanish, since the corresponding coefficients vanish due to the presence of identical columns in the determinant defining them. When checking the condition alpha for the vector parameters v j lambda and w j lambda, it is convenient to use rather simple sufficient conditions. Lemma 3. For a fixed index j from 1 to n, the inclusion m of vj belongs convex hull of m day and omega sub j. The inclusion star holds. Lemma 4. For a fixed index j from 1 to n, the inclusion double star holds. By construction, the inclusion 38 are valid. The next page. The following sufficiently convergence.
Sorry.
No.
This one?
The previous. The following sufficient conditions of root function completeness take place. Theorem 1. If there exist n linearly independent vector parameters gamma 1 of lambda, gamma 2 lambda, and so on gamma n of lambda from alpha, then the root function system of the pencil L of lambda is n-fold complete in L2, 0, 1 with zero defect in the case kappa I less than and or equal n minus 1, I from 1 to n, and with possible finite defect otherwise. Corollary 1. If conditions 39 and 40 are satisfied, then the root function system of the pencil L of lambda is n-fold complete in L2, 0, 1. And theorem 2, if there exist m pairs of vectors VJS, WJS, S from 1 to m, such that VJS and WJS from alpha, then the root function system of the pencil L of lambda is m-fold complete in the in L in L2, 0, 1 with finite with possible finite defect. The next. The case of a pencil when characteristic lies on two rays and splitting boundary conditions. It's an application of the previous theory. In the space L2, 0, 1, we consider an ordinary differential polynomial pencil L1 of lambda generating by differential expression L of y lambda of the form 41 and linear independent homogeneous two-point splitting normalized boundary conditions 42, 43. 44 at the point 0, 43 at the point 1, where the parameters satisfy the conditions 44. Let us assume that the characteristics omega 1, omega 2, and so on, omega n are pairwise distinct, non-zero, and lie on the two or one rays emanating from the origin in quantities k and n minus k. K from 0 and n implicitly. The next. The 45 is the inequality for characteristics. It's better to see the figure 3, how characteristic lie on the complex plane. The one ray is the real axis, and the next the ray of the angle phi. The next. The study of multiple root function completeness using classical generating functions. To formulate the theorems, we introduce the following notations: 46, 47, 48, 49, 50. The next. Lemma 5. The classical generating functions g I of x lambda satisfy condition alpha if a maximum of k and n minus k is less than or equal L, I from L plus 1 to n under the condition 47 and 49. B, minimum of k and n minus k is greater than or equal L when I from 1 to L under the conditions 48 and 50. And at the same time, the estimate 51 are valid for sufficiently large module lambda. Remark 1. In the case minimum of k and n minus k less than L, less than maximum k and of k and n minus k, 45, it cannot be guaranteed that gi of x lambda belongs alpha for some I from 1 and so on to n, that is using the classical generating functions j of j y of x lambda I from 1 to n, it's currently not possible to establish the multiple root function completeness for the pencil L of 1 lambda. This situation has not been previously identified in the study of the multiple root function completeness in the pencil L of L1 of lambda. The next. Theorem 3. If maximum of k and n minus k is less than L, is less than or equal L, and condition 47 and 49 are satisfied, then for m equals m multiply by n minus L, the root function system of the pencil L1 of lambda is m-fold complete in the space L2, 0, 1 with possible finite defect. Theorem 4. If minimum of k and n minus k is greater or equal L, and conditions 48 and 50 are satisfied, then for m equals to L, the root function system of the pencil L1 of lambda is a multiple complete in the space L2, 0, 1 with possible finite defect. If the case, which not in theorem 3 and theorem 4, the case when minimum of k and n minus k less than L and less than maximum k of k and n minus k, reasoning using only the classical generating functions does not work, since the classical generating functions do not satisfy, generally speaking, the condition alpha. It turns out that in the case of 52, one can construct generalized generating functions satisfying of the alpha condition, thereby implementing the PMC scheme and obtaining conditions for the multiple root function completeness for the pencil L1 of lambda. The next. Study of multiple root function completeness using generalized generating functions. Let us consider, let the condition 53 be satisfied. Further, for the definiteness, we consider then n minus k less than k, n minus k less than k. In this case, the polygon M is a quadrangle A prime, B prime, C prime, D prime, which is a parallelogram, figure 4 and 5. The figure are given for the case n minus k less than or equal k. The next page. The polygon A prime, B prime, C prime, D prime is M. The previous page. In the case of n minus k less than or equal k, we will conventionally call the side A prime, B prime, and D prime, C prime the long sides of the parallelogram A prime, B prime, C prime, D prime. In reality, these sides can actually be shorter or longer than the side A prime, D prime, and B prime, C prime. It depends on the values of the characteristic line on the A prime, B prime, and A prime, D prime. The terms longer means only that the sides A prime, B prime, and D prime, C prime are generated by no fewer characteristic than the sides A prime, D prime, and B prime, C prime, due to the fact that the n minus k is less than or equal k. In this case, the sites A prime, D prime, and B prime, C prime will be called short. In the case k is less than or equal n minus k, on the contrary, the sites A prime, D prime, and B prime, C prime will be called long sites, and the sites A prime, B prime, and A prime, D prime will be called short. The next. The next. To formulate the obtained results about the multiple root function completeness for the pencil L1 of L, we also need to polygon M n minus L, which is convex hull of those points of the set omega that are sums of different characteristics in the amount of exactly n minus L terms. In the figure 4 and 3, the set M n minus L is a polygon ABCD, the boundary of which is indicated by a solid thick line. In the case n minus k is less than or equal k, the vertices A and B lies on the long side, A prime, B prime, on the parallelogram M. Vertices C and D lie on the long side D prime, D prime, C prime on the parallelogram M. Lines A, D, and B, C are broken line. The vertices of the polygon M n minus L lying on the long sides of the parallelogram will be called the main vertices. Previous page. A, B, the polygon A, B, C, D is a polygon M n minus L. And the A and B lies on the line A prime, B prime. DC lie on the long side D prime, C prime. The next. The next. It is shown that in the case of splitting boundary conditions, 44, 43, the inclusions M delta includes M n minus L is valid. It follows from the condition 53 that the polygon M n minus L and hence the characteristic polygon M delta does not touch the short sides of the parallelogram M. Previous page.
Which one was it?
Previous page. Previous page. When figures. You see the polygon I, A, B, C, D don't touch the sides A prime, D prime, and B prime, C prime. The next page. The next page. We formulate the main theorem, theorem 5. If the inequalities 43 are satisfied, M equals minimum of K and N minus K, and the characteristic polygon M delta of the pencil L1 of lambda contains the principal vertices of the polygon M and N minus L, then the system of its root function is M multiple complete in L201 with possible fine defect. This result of this section are published in the detailed in the article 2. The next. completeness of the root function system of a differential operator generated by simplest fifth order differential operator and two-term two-point boundary conditions. In the space L201, we consider the linear ordinary differential operator L0 generated by the simplest differential expression of the fifth order 54 and two-term boundary condition 55, where coefficients are complex numbers and modular alpha nu plus module beta nu greater than 0, nu from 1 to 5. The interest in this operator is caused by the fact that with an appropriate choice of coefficients alpha nu and beta nu of the boundary condition 55, this operator can be Birkhoff regular, weakly irregular, and strongly irregular. That is, this operator is a good model operator for which the classical generating functions do not satisfy the condition alpha, but for which it is possible to construct suitable generalized generating functions satisfying this condition. The next. It is shown, the next.
Next.
Previous.
This one?
The previous. The next.
The next?
The next. The main result, previous. The main result is that gives the theorem 6 gives the main result. Suppose that either alpha nu is not equal 0, nu from 1 to 5, or beta nu is not equal 0, nu from 1 to 5. Then either the root function system of the operator L0 is complete in the space L201, or this operator is degenerate, that is, either it has no proper eigenvalues at all, or it has a finite number of eigenvalues, or all lambda from in complex plane are its eigenvalues. These results are announced in 2002. Later in 2009, a more general result was obtained for a differential operator defined by a differential expression of arbitrary order n equals 2m plus 1. M is the natural number from set n. This result is published in detail in the paper 3-4. The study of the general cases is very cumbersome and becomes of this its essence may not be very clear. For a better understanding of the idea of the method, it seems convenient to consider the simplest case n equals 5, which preserves the difficulties of the general case. The proof of the main results of this section on the root function completeness for the operators L0 is carried out in accordance with the PMC scheme, but not for the operator L0, but for the closely related pencil L0 of rho equals L0 plus R fifths identical operator, where L equals minus R fifths generated by the differential expression 56 and the same two-term boundary condition 55. The next.
Ведь осталось 5 минут.
Yes, I have that. I have not enough time. And the next. I only the main details show. The next. The next. It's in the figure 6. We see the characteristic polynomials for different cases: Birkhoff regular, weakly irregular, strongly irregular. The next. The characteristic determinant has the form 63. And if the coefficient delta 1, 2 equals or delta sub 1, 2, 3 equals, we can obtain the different case of irregularity. The next. This is classification of the pencils in the point of view of irregularity. We introduce the classes NR0, NR0, sub-zero, super-zero, NR0, super-zero, and so on. And for us is very important the irregular cases which one, the case 1, 1, 0, 1, 1, and two classes 2 is degenerated pencils. The next. This is the main lemma which allowed us to solve the problem under consideration. 66. The vectors are cyclically shifted. It's very important. The next page. The lemma 10. In lemma 10, described analytically the irregular, strongly irregular cases. 68, 69. The next page. The lemma 11 gives the vector parameters which belongs to alpha. We have the two case S fifths is not equal 1 and the general case, and S fifths power equals 1, the degenerate case. We also consider also the case 70. The next. This is the characteristic polynomial, and the polynomial M gamma sub 1 super 1 dashed line dashed line, and which satisfied alpha condition alpha. The next. No, it's the general case 7, the operator L0 in the when n equals 2m plus 1 and the boundary condition 73, 74. The results of this section are published and detailed in the paper 3, 4. The next page. It's the references. This is references, and the next page. Thank you for attention. Excuse me for the problem with my with showing my presentation, because I don't understand what that button show demonstration is absent in my screen. Thank you very much for attention.
So thank you very much for your talk. Please, any questions? So if no questions, we have to thank the speaker for the interesting talk. Thank you very much.
Thank you.
So our session is over. And we have to say goodbye and see you tomorrow.
Okay, so if there are no any further comments, then I will close the session. Okay.
Okay. So bye-bye.
Bye bye.
Bye bye.